has spent over 15 years as an optical systems engineer and program manager for this project. And she has also contributed to the Hubble Space Telescope science instruments and manages the Ball Aerospace contribution to the Large Synoptic Survey Telescope. She was the recent 2004 recipient of the Women in Aerospace Achievement Award, and she is also involved in education, inquiry-based learning, STEM, and educational equity and opportunity. Please help me welcome Allison Barto.
All right, good morning, everybody. I'm so happy to be with you guys. It's fantastic that you guys have an organization like SEDS while you guys are in school. I definitely wish we had something like this when I was going through school myself. As mentioned, I'm going to be talking about the James Webb Space Telescope. If you guys want to know more or follow us on Twitter and Facebook, those are all of the handles. All right. Now, you guys are all interested in space. I don't need to tell you why it is we observe space. You know, it's really the oldest of the sciences. When we go out at night and look up at the stars, it's awe-inspiring, it's humbling, and it makes you want to know more. And so from the beginning of time, humans have been looking up at the sky and trying to make sense of what it is that they see. And we did pretty well for a while. Saw the planets, kind of were able to predict where they went. And then we really revolutionized our understanding when a little over 400 years ago, Galileo invented the first telescope. And when he looked up at the stars, he saw all sorts of things that were not supposed to be there. This was not what space was supposed to look like. He looked at the moon, and there were all of these mountains and craters, just like here on Earth. It was supposed to be a perfect sphere. Everybody knew that. He looked out at the other planets and saw moons orbiting them. Everything was supposed to orbit us. And this is the great thing about scientific inquiry and doing these experiments is you don't know what you're going to see, and you have to accept it when we have these kinds of observations. And so when Galileo looked at the sky and saw all these things that were not supposed to be there and kind of revolutionized our understanding as humans of our place in the universe. And of course, like any good scientific experiment and question, it only begat more questions. And so the race to build ever bigger telescopes ensued so that we could learn more and more about where we were. And this continued through the 20th century, building ever bigger telescopes on the ground. We went from large refracting telescopes using Galileo's design to Newton's reflecting telescopes that let us build even larger telescopes. You guys can all feel really lucky that you live now and you don't have to be like that guy in the center of the rightmost picture. Can you see him? He's in the very center of that cage, and he had to ride around with the telescope. And his job was to change the glass plates so that we could take pictures. Very nice that we don't have to do that anymore. But there's a problem with building telescopes on the ground, and that is that there's a few things we can't get past. The first is that we have to look through the atmosphere, and that blurs the images of what we're looking at. We can't get past that. We're doing pretty well with adaptive optics. We're able to do better than we could, but there's still a fundamental limitation there. The other limitation that we definitely can't get around on the ground is the fact that not all the light makes it down to us. Light in many wavelengths is absorbed by the constituents of our atmosphere. So we're not able to see anything in the gamma or ultraviolet from space if we're observing from the ground. Similarly, we can't see anything in the very long radio waves, and a lot of the infrared spectrum is also invisible to us if we're observing from Earth. And so in the early 1900s, we realized if we really want to understand everything that there is to know, out there, we need to observe from space. And in 1946, Lyman Spitzer proposed a space telescope, which we all know today has eventually become the Hubble Space Telescope. And in thinking about why do we need to observe from space, NASA set off on a bold mission to fill in all of these wavelength gaps with what they called the great observatories. So we had the Compton Gamma Ray Observatory, the Chandra X-ray Observatory, Spitzer that observes in infrared, and of course the Hubble Space Telescope that we all know and love. And I'm lucky enough to work at Ball Aerospace in Boulder, Colorado, where we had a role on all 4 of these great observatories. Now, just like with Galileo, any good question just makes us wonder more. And coming off the discoveries that we've had with those 4 great observatories, as well as the planet finding mission Kepler, large ground-based observatories that have come online, we still have a lot of questions. The origins of many aspects of the universe is really what we're still yearning to get a little bit further knowledge on. We want to understand, how is it that galaxies evolved to what we see today? If we look far back at the earliest galaxies that we can see with our present telescopes, they look kind of blobby. And the newer ones have this beautiful structure that we're used to looking at. We still don't understand quite enough about how stars form and how protoplanetary disks form. And even more exciting, we want to be able to understand the origins of life on planets. And so really the holy grail is becoming, with JWST and telescopes that are going to come later, is can we detect signatures of life on these extrasolar planets? And so with all of these questions in mind, NASA embarked on the next generation flagship observatory, the James Webb Space Telescope. Now I'm going to talk today a little bit about how we got to where we are today on the telescope. Why does it look the way it does? And what is that design process that we went through? The James Webb Space Telescope is an international collaboration led by NASA. There's contributions from the European Space Agency and Canadian Space Agency. I'm going to spend today mostly talking about the telescope itself. The telescope itself is primed by Northrop Grumman out of Space Park, California, with contributions of the composite structure from ATK. Harris did the optical INT for the telescope, actually putting all of the pieces together. And at Ball, we built all of the optics. So all of the mirrors that you see there, the primary mirror consists of 18 individual mirror segments. There's a few other mirrors to relay the light and get it back to the science cameras. I'm really going to talk about that architecture of why does this observatory look like it does. So this is a telescope like any other. The light bounces off the primary mirror, hits the secondary mirror, and then goes into the center black thing that you see there. It's called the aft optic system. There's a couple more mirrors in that relay the mirror back to the science cameras that sit behind the telescope. So whenever we're designing a space mission or any instrumentation for scientific discovery, we start with the science questions. What is it that we're trying to do? So one of our goals with the James Webb Space Telescope is to see very faint objects. We want to see the very first generation of luminous objects after the Big Bang. So we need to look back in time over 13.5 billion years. And if we're looking back that far, we are looking at things that are very faint. We're counting photons to try to image these very ancient objects. And if we want to see very faint objects, the first rule is that we want a really big mirror. The larger the mirror, the more photons that will hit it, and the fainter the object that we'll be able to see. So that's a pretty easy solution. We want to see faint things, we build a very large mirror. So this is the Hubble Space Telescope mirror, 2.4 meters in diameter. You can see a couple people in there for size reference. on a similar scale, these are 2 of the 18 mirrors that make up the primary mirror of the James Webb Space Telescope. And the entire telescope integrated, you can see down on the lower right, there's a guy walking for scale. So this is the largest space telescope and largest and most complex space telescope that has ever been designed. There are telescopes that are larger than this on the ground, and we're certainly working to build extremely large telescopes on the ground. And we can do that, but we have a problem with space. And that's that we have to be able to fit this thing in a rocket and get it up there. So our mirror is too big to fit in a rocket. That's a problem. So, of course, we always have a solution. We have what we call the origami telescope. We have to fold our telescope up in order to fit into this rocket. And then as we deploy out to our final orbit, we unfold the telescope robotically and then align all of its mirrors. So we have this basic solution. We're too big to fit in the rocket, so we unfold. Something happened to my charts that are in the wrong order, so I'm going to skip past this next one. We'll go with it. Okay, so the other problem, though, is that if we fold up and we get in a rocket, this is great, but launch is really violent. Everything is going to move and shake, and we have these 18 mirrors that have to be precisely aligned to each other in order to act like one large mirror. And when you're building an optical system, the things that determine its performance are twofold. One is the shape of each optic, and the second is the alignment between those optics. So this is the picture that we're going to see when we first image through our telescope. It looks like maybe we're looking at an interesting field of a few different galaxies or nebula. That's not what we're seeing here. This is a picture of one star, but we have 18 misaligned and out of focus mirrors. This is clearly not what we want to do if we want to have good science with the observatory. So in order to deal with this issue, we have what's called an active telescope. We have actuators and motors on the backs of each of the mirrors so that we can move them in 6 degrees of freedom, as well as change their curvature so that we can align when we're in space. In the upper left, you can see bipod pairs of our actuators, and then there's some pictures of our technicians at Ball installing these actuators. Now, just to give you an idea of scale, right? The challenge with JWST is that it's at the same time really, really big and needs just extreme precision. So our actuators have to operate over a range of about 25 millimeters, which is big. I know it seems small, it's big, because we need to align each of our mirrors to each other to about 7 nanometers. So our step size on each of these actuators is 7 nanometers. To give you a scale, if you've got a piece of paper by you, you look at that piece of paper. I've got one. All right. This piece of paper here is about 100 to 200,000 nanometers thick. And our actuators have to position our mirrors in 7 nanometer steps in order to align them well enough to meet our science goals. And so we developed this actuator system at Ball, and actually we had a couple interns who were very involved in designing it. So you can have amazing contributions even when you're not through with school yet. Okay, so we've gone through this basic challenge, right? We want to observe really faint objects, so we need a big telescope, which leads us down the line of needing to fold it up and needing to be able to adjust everything and make this really complicated system. What else do we want to do? What else is the science asking us? We have science goals to observe star birth, look for signatures of life around extrasolar planets, and observe that first generation of stars. And for any of these sciences, I need to be able to observe in the infrared. So for example, we have a picture here of a nebula where we can see that beautiful shape of the cold dust. But if we look in the infrared, we can see through that cold dust and see the star-forming regions within it. So for this reason, if we want to understand star birth, we need to look in the infrared. Similarly, if we want to look for signatures of life in the atmospheres of extrasolar planets, which is extremely exciting science we didn't even know to design to when we first started building the James Webb Space Telescope, because we hadn't detected any extrasolar planets yet at that point in time. At any rate, for the very same reasons that we cannot observe on the ground in the infrared because it's absorbed by the constituents of our atmosphere, that's the same reason we need to then look in the infrared if we're looking for signatures of life on other planets, because we want to see the signatures of those chemicals in our atmosphere. As life as we know it requires water, so we want to look for water. And then we also want to look for byproducts of life like carbon dioxide and methane. And if we see ratios of these constituents in the atmospheres of exoplanets, then that's a good sign to us that there could be something really interesting going on there that we would want to then follow up with an even larger telescope in the future. And then finally, to observe that very first generation of stars, we need to look in the infrared, because as the universe has expanded, light coming from those stars has been redshifted. The wavelength's been stretched out as the universe has expanded, and so signatures that we might previously have seen in the optical are now going to be in the infrared. So for all these reasons, we need to look in the infrared. Okay, this seems pretty straightforward, but like all of our problems, every time we have one solution, it only causes another challenge. And that is that warm objects emit in the infrared, right? So just like we saw that we could look inside that cold dust to see the warm stars, we have the same problem that if, for night vision goggles, for example, you can see through something cold to see the warm heat signature beneath it. But here's the problem. If warm objects are emitting in the infrared and our telescope is warm, like most telescopes that we have out there, then all we're going to see is the glow of the background of this telescope, instead of seeing the very faint signals that we're looking for. So that means that we have to take this entire telescope and cool it down, which is a challenge if you have something this big. We're used to having infrared instruments. You might have a cryocooler or some other mechanism to cool down a specific instrument. To do the science that we want to do, we have to cool our entire 22-foot wide telescope. So we do this in a few ways. You can see the picture of the Earth on the left with the yellow line showing about the orbit of the Hubble Space Telescope a few hundred miles overhead. What we do, if we do that, then we're going around the sun and we get warm and cold and warm and cold, and we're never going to cool down. So we go out to the second Lagrange point, which is about 1 million miles away, 4 times further than the moon. And this point is located on the far side of the Earth from the sun. And then we orbit around the sun with the Earth. And by putting ourselves in this orbit, it means the hot things in the sky, the Earth, the sun, and the moon, are always on one side of us. And that allows us to build a giant sunshade. That's this multi-layer item that you see at the bottom. It's about the size of a tennis court. And we can use that to block all of those really hot items. And then the telescope just looks into deep space, which is about 7 Kelvin. And it lets us cool passively down to 35, 40 Kelvin. So we're able to cool ourselves significantly. The temperature difference between the warm side, where the spacecraft is on the bottom of the sun shield, where we have our solar panels and our communication and all of that, the difference between that and the cold side, where the telescope is around 500 degrees. So we have a significant temperature drop. And then again, though, we have another problem. Now we're designing this entire telescope to work at cryogenic temperatures, and we need to make sure that we have the performance we need at those temperatures. So what we talked about before, right? If we want to have good optical performance, what matters is the shape of your mirrors and the alignment between them. We talked about the alignment. We have actuators, so we can adjust that alignment on orbit, but we need to worry about the shape of each individual optic, which will distort when we go cold. So just like you need to worry about, maybe if you live in a cold climate, in the winter your doors don't close right, that sort of thing. Well, we have to worry about that with our mirrors. And most standard materials change their shape rapidly at cold temperatures. So there's two problems we have to worry about. One is we're going to make something at room temperature, and then it needs to work when it's really cold. So there's just this bulk temperature change that's going to happen. The other problem we have is that we need it to hold its shape very well as we look at different parts of the sky. And there's about a 1 to 2/10 of a degree temperature difference between looking at the galactic plane, where there's lots of items that are close by to look at, and looking out of the galactic plane at deep space. And it turns out just that 1 or 2/10 of a degree difference is enough to put us out of performance requirements, and we wouldn't be able to see the things we're looking for. And a lot of materials that we're used to using, they behave really well at room temperature. If we're a few degrees hot or cold, it doesn't matter. That's why there are standard materials. But they often change shape very rapidly for small temperature differences at cryogenic. So what we did is we chose to make our mirrors out of beryllium. The beryllium has a few benefits, and one of those is that it is very stable at these cold temperatures. So it does distort a lot between room temperature and cryo. For example, we have a bench that's maybe 6 feet long, and it'll change its length by about 3 millimeters going cold. But once it gets cold, it's very stable, and we could be off on our thermal predictions by 25 degrees, plus or minus 12 or 13 degrees, and it wouldn't make an impact on science performance. So how do we make beryllium mirrors? We start by mining beryllium in Utah, and they mine this beryllium and they turn it into a really pure beryllium powder. While it's very repeatable going cold, that's if you have just pure beryllium. And if there's anything else in that material, now it's not going to behave quite the way we expect. So we need to make it very, very pure. And then we take this pure powder and we put it in a big can, and we heat it up and we press on it and turn it into a solid piece of beryllium. And then we cut it off, and this is what we're left with. So the other challenge of launching something this big into space, as you guys all know, is that big equals a lot of mass, and it's hard to launch heavy things into space. One of these segments that we have here that you see on the right, one of the blanks for a mirror, weighs about 500 pounds. And if we were to launch 18 of these, plus the whole back plane and all the rest that goes with it, we would have a really hard time getting out to L2. So the other property of beryllium that's excellent is its stiffness and its strength, and we're able to lightweight it by hogging out most of the backside. And we take these mirrors from 500 pounds down to 50 pounds. We remove 92% of the material in this process. If you look really carefully at this picture, you might be able to notice that those ribs are not all the same thickness. So we needed to very carefully design ourselves into this space of making sure we're light enough to be able to launch, while also have enough structural integrity that we don't change the shape of the mirror due to that launch. And so we actually individually tuned the thickness of each of those ribs on the backs of the mirrors based on where they were on the mirror and where the load path was, so that we could get as much mass as possible out of the system while still preserving optical performance. So after we take away most of the material, then we need to create a nice smooth surface. So we start polishing it, polishing the front side, which, by the way, the face sheet is just a few millimeters thick. So we start polishing that, and we get it so that it looks pretty good. It looks about like the kind of mirror that we would want. But remember, everything changes shape going cold. So then we take all of our mirrors, and we went in groups of 6 and tested them at 30 Kelvin at the XRCF facility at Marshall Space Flight Center. So you can see a guy there helping to guide and pull in that large structure that's holding 6 of our mirrors. And we take them down to 30 Kelvin and look at them interferometrically, and we're able to see how they distort. And you can see in this picture that there's all sorts of lumps and bumps and valleys. Red is a high spot, blue is a low spot, and this is a problem. Our mirrors, we need to figure them to about 20 nanometers RMS. What does that mean? What that means is if you were to have one of these mirrors and you were to imagine that it was the size of the United States, we need to have a mirror that is smooth enough that you wouldn't have a mountain or a valley larger than about 3 inches. So that's how smooth they need to be. And remember, they need to be that smooth at cryogenic temperature, not when they're warm at room temperature where we're polishing them. So we take them cold and we look at how they distort. And luckily, because we have this very pure optical grade of beryllium, we know that they're going to distort the same way every time. So we're able to use this map and essentially polish in the inverse of what we see. So if we cool the mirror down and it pops up in the middle, and there's a lump there, we go at room temperature and we'll polish a little valley into the mirror in that spot. And then the next time it cools down, that little valley will pop up because we knew it wanted to pop up in that spot, and it will be nice and smooth. And so you can see this process works. On our first mirror, we tested it a few times just to make sure it really did have the consistency of performance that we needed. And indeed they did, which was really fantastic for our process because it meant we only needed to test them cold once to make sure that we were going to hit our final performance requirements. So we bake the mirror, we polish it, we test it cold, we polish it again to make sure the figure would work at cryogenic temperatures. Then we coat them with gold. Gold is highly reflective in the infrared. And then just to make sure, we test them all again. Here's the setup that we had at Marshall Space Flight Center. So making each of these mirrors took about 5 years, a little over 5 years per mirror. And we employed folks from all across the country. You can see here a map of the general path that each mirror took during this construction process. And pulling together all of these different industry providers across the country was really fantastic to see how they all work together. When we're building scientific instrumentation for space, usually we build one of something. And so needing to have a kind of an assembly production sort of approach to this was really something new. And we had to develop all of the production facilities at most of these vendors who had all done space optics before, but nothing this big, and certainly not 18 of them. So it was really an effort to build up the entire infrastructure that we needed to build these mirrors. Now, I've talked a lot about the mirrors. James Webb is unique for many reasons. It's, as I said, the largest and most complex space observatory that we've built. But additionally, it has many new technologies. We had 10 official new technologies that we had to bring from a very low TRL level up through flight readiness. And normally when we launch a space program, it's very expensive and it's hard to fix things. In fact, we're going 1 million miles away. We can't do what we did with Hubble. We can't send astronauts out there to fix this. We've never sent people that far. So we need to know it's going to work. And so usually we might have 1 or 2 brand new technologies that we're bringing to market in an observatory, but we had 10. And we invested early in all of these technologies. So I'm not going to go through all of them, but we had a number of them, from cryogenic stable structures, the materials that we needed for that large sun shield. We have cryogenic system for actively cooling our mid-infrared instrument that needed some development. All of the detectors, we developed these detectors in the early 2000s. They've since been used on other telescopes. Although we developed them for Webb, it's taken us so long that other people have then pathfinded them in the field for us. The way we figure out how to align all these mirrors on orbit, we use only the images from the science camera. We don't have any other active feedback telling us where one mirror is relative to the other. So there's a number of technologies we needed to develop to get to the point of being able to launch this observatory. So where are we today? The full telescope is assembled. This is a picture of it at the Goddard Space Flight Center, taken about a year ago. We went through system level, telescope and camera level environmental testing. So inside that giant rectangular shroud there is the telescope with all of the science cameras. It's being loaded onto a giant shaker table out at Goddard, where we went through vibration testing and then acoustic testing. And then we took the telescope down to the Johnson Space Center in Houston. This is a picture of their Chamber A, which was used originally for Apollo testing. You can see a couple people there in the doorway. It's a 40-foot diameter door. It's the largest single hinge door in the world. Little fun fact. The whole chamber is about 7 stories tall, and we put a extremely large helium shroud inside of that chamber so that we could do cryogenic vacuum testing, just like we did with those mirrors at the Marshall XRCF facility. So here you see the telescope sliding into the chamber. And I like this picture because if you guys remember the original Willy Wonka movie, anyone see the original movie? And they had the Wonka vision. Remember the Wonka vision where they took that little candy bar and made it a giant candy bar? Anyways, I always feel these people look like the Oompa Loompas in the Wonka vision. So after sliding it into the chamber, we close the door to do our cryogenic testing, and it takes an entire month to cool this observatory down. So we spent a month just cooling down, about a month testing. That testing did coincide with Hurricane Harvey in Houston. We tested through the hurricane, and then about a month to warm up again. And so we've completed that testing so that we could verify that the optical systems worked. There's another interesting discussion is how you test something of this scale that you're going to launch, because you cannot test it completely as you're going to fly, which is, of course, what we want to do as much as possible. That's a whole nother talk. So at this point, we've finished the testing. We're still in the chamber, but the door is open. We next ship the observatory to Northrop Grumman, where we mate to that sun shield and the spacecraft. From there, the observatory will go onto a boat, and it will go down through the Panama Canal over to French Guiana. One of the European contributions to the Webb Telescope is the launch vehicle. We launch in 2019 from French Guiana, and it will take us about 6 months to do all of the commissioning, all of the alignment, and deployments in space before we start getting our first images back. And of course, just like anything, we always know that answering one scientific question brings us to the next question. So we're already talking about what comes next after Webb, because while we know we're going to be able to do some of this early cosmology, see this first generation of stars, start to look for signatures of life around extrasolar planets, we're not going to be able to see those signatures in the atmospheres of other planets around very small planets. And we'd, of course, like to do more than just say, what's in this atmosphere. We'd like to be able to image those planets. So we're already talking, as we develop the next decadal survey recommendations for astrophysics, about even larger telescopes. And as we talk about larger telescopes, there's a few options. One is we're looking, as we have larger launch vehicles coming on board, how much bigger could we make a telescope that will fit into these larger launch vehicles? And we can get up to maybe 15 meters or so, which would be a dramatic improvement. You guys might hear about large telescopes we're building on the ground, the 30-meter telescope that's going into Hawaii, even larger telescopes that they're building in Europe. There's, in addition to the wavelength regime issue, that obviously those telescopes still have some wavelengths that they're not going to be able to interrogate being on the ground. You can give yourself also, just to understand the difference of being able to look from space or look from the Earth, there's about a 4-to-1 factor. So if I have a 10-meter telescope in space, that's going to be about equivalent to having a 40-meter telescope on the ground. So as you hear about those telescopes, you think, gosh, Webb seems really small. There is that factor to keep in mind. So if we could build a 15-meter telescope in space, that's larger than anything that we've that we're close to having on the ground when you factor that in. But it would be even better if we could build something larger than 15 meters. I mean, if we could really image something in space, that would be amazing. And so that's where we need to start thinking about looking back at the Hubble paradigm, where we do have this intersection between the science and the exploration programs in NASA. And what could we do to assemble a telescope in space, and what would that look like? So we're also looking at those details as you guys talk about future space economies. There's definitely a realm out there for the science side as well that would help. All right, thank you guys. And I think we have time for maybe a couple questions, if there are any. Yes?
You talked about micrometeoroid protection for years of life.
Great question. So he asked if I could talk about micrometeoroid protection. Micrometeoroids are absolutely a concern. Very, very small, high energy particles. So our sun shield is 5 layers thick. And if you do the calculations of the energy of those micrometeoroids, we'll absolutely have impacts that go through 1 layer of the sun shield, but we won't have any that can get through all 5 layers. And as long as that can't happen, then we're protected, because each one of those layers of the sun shield is going to drop us by another 100 degrees. So if we had a straight line through, then there would be a really hot spot, which would be a challenge from a stray light perspective. Then on the mirrors themselves, we absolutely have to account for the impact of the micrometeoroids. The main impact that they'll have is that we'll lose surface area, collecting area, as time goes on. We have 25 square meters of collecting area, and we factor in to our calculations the fact that we won't be getting as many photons back later on in the mission, because we'll have chipped off bits of the coating because of those impacts. The other really fascinating impact of the micrometeoroids is that there's enough energy there that our mirrors will actually change shape over time. Due to being bombarded by those micrometeoroids, the curvature of each individual mirror segment will actually change. However, since we have a radius of curvature actuator and we can actually change the curvature of each mirror, we're going to be able to compensate for that. Yep?
What would the next step be in the event of a catastrophic failure at launch?
What would the next step be in the case of a catastrophic failure at launch? I think we would cry. That would be the first step. With any failures, launch failures, when you're building one of something, it's a possibility that's going to happen. We don't have another telescope waiting in the wings. I think that if there were a failure at launch, that would inform the discussion about the next telescope. Right? A telescope like this is a huge investment. This is an $8.8 billion telescope. And if we fail at launch, we've lost all that. We obviously have the the benefits of everything we've learned along the way, the advancements in technologies that will factor in, but we won't have the observatory. And so there is a question, just like we talked with the recession, about banks that are too big to fail. Is there a mission where, we just can't take that risk of putting that much up there at once? And so I think that if there were a launch failure, there'd be two questions. One is, do we have the stomach to try something like this again and take that risk? And the second is, should we put more emphasis into thinking about the in-space assembly of future telescopes where you don't have as much risk with each single launch? Yep. How do we deal with the waste heat from electronics? I didn't talk about the electronics a lot. The interesting thing here is normally, right, we want our electronics, they operate warm at room temperature. So what do we do when we need to move around all these segments on this mirror? So what we actually did is originally, right, the easy approach is that you have all the electronics in the spacecraft and you send a bunch of wires up to the telescope and they move everything around. And the parasitic heat from all of those cables, we'd have, I don't know, over 4,000 cables just for the mirrors going up from the warm spacecraft to the cold telescope. That would have been a huge problem. So we developed electronics for the mirrors that operate at 30 Kelvin. And we were able to find commercial EEE parts that were able to survive a cryogenic radiation environment. And we're able to design for that, which was really fantastic, because normally you would have to develop your own custom ASICs in order to handle the cryogenic environment. That's what they did for some of the detectors on the cameras. Even with that, even with keeping our electronics very cold, there is still a concern. And one of the unfortunate pieces of our design is that the electronics for the cameras, although the detectors themselves can operate cold, the camera electronics still do operate warm. And they have to be located close to the mirrors. So on the back of the telescope, there is a warm compartment. And what we do is we have a lot of radiator surface. Basically, the whole back of the center of the telescope are radiators to cool the instrument electronics. I don't know how many square meters overall we have, but these are 10 by 6 foot radiator panels that are coated with materials to reject heat well in the infrared. Yep. Yeah.
You said you used beryllium. Beryllium metal or ceramic?
Metal, pure beryllium. So you'll hear other materials, and Albumet and other materials that utilize beryllium in them are used, but we just use the pure beryllium, which is a metal. I think that that's all the time we have for questions, but I'll be around for at least the first half of the day if you guys have any other questions. Thanks.